So we are going to differentiate e to the minus x times sine of 2x. And this is a product of two functions, so we're going to use the product rule. So the first one here, e to the minus x, is going to be u, and that means that du by dx is going to equal minus e to the minus x. So I differentiated the minus x, which gives me minus 1, brought it down, and then the rest stays the same. And similarly, v is going to be sine of 2x, which means that dv by dx is going to be 2, because that's the differential of sine 2x, times cos of 2x. And now I can substitute into the product rule, which is dy by dx is equal to u times dv by dx plus v, which is sine of 2x, times du by dx, which gives me that. And I'm going to tidy that up. I'm going to take out a factor of e to the minus x, and that leaves me with 2 cos 2x minus sine of 2x, like that. So there we are, we've got our gradient function now. What next? Well, hence show that the curve has a stationary point when x is a half of arctan of 2. So that could be a little bit intimidating, I imagine. So it's important to remember that arctan of 2 is the same thing as saying the inverse tan of 2. Okay, so it's nothing you haven't seen before, it's just written slightly differently. So, stationary point. So that's when dy by dx equals 0. And if we look at dy by dx, then we know that the e part of it can't equal 0, but this bit can. So it's when 2 cos of 2x minus sine of 2x equals 0. And hopefully you can see that we're going to get a tan out of this fairly straightforward. We're going to add the sine 2x over, so that leaves us with 2 cos 2x equals sine of 2x. Then we divide by cos, which gives us sine of 2x divided by cos of 2x, which of course is the same as tan of 2x. Therefore, let me just move it down a bit, if tan of 2x is equal to 2, then we take an inverse tan of both sides, or I should say here an arctan. So we've got 2x is arctan of 2, and that means that x is a half of that, which of course is what we're trying to show in the first place. And there we are. Question 2. Little trig proof here. Show that this lot is equal to tan theta. So hopefully you're noticing that we've got double angles here. So the formula we're going to use for this, sine 2 theta is equal to 2 sine theta cos theta, and cos 2 theta, a lot of choice here. we're going for 2 cos squared theta minus 1. So there's our identities we're going to use. Now, just a brief word of this. How do we know it's double angle? Well, we've got the 2 theta there. That's a clue. The fact that we're going for theta here, we're going from double angle to single angle. That's a really big clue, because these are the sets of formulas that convert double angle, 2 times whatever it is, to single angle. And there's several options here, and all I can suggest is if you're not sure why I went for this one, then you have to be prepared to experiment. If you sit there and try and do it in your head, you won't be able to. You've actually got to try some stuff out with these problems. So here we go. Sine of 2 theta, and I think it's perhaps reasonable to realise that I'm not doing this blind. I have worked these out before I do this video, so you're not seeing my process of thought of how I arrived at this particular route to the solution. So sine 2 theta, 2 sine theta cos theta, and then on the bottom. Now, I'm just going to rearrange this one here, because if you notice, if I add the 1 across, so cos 2 theta plus the 1, I get 2 cos squared theta. So you can see that actually I can replace the whole bottom bit with 2 cos squared theta. And that, of course, is useful because it means that I can cancel the 2's now, and in fact I can cancel the cos, which leaves me with sine theta over cos theta, which happily happens to be tan theta, which is what we're trying to show. And that's why it's only a 3-mark question. It is worth remembering, though, that a lot of A-level maths teachers will present to you solutions that they've already worked out, partly to save you time, partly because they don't want you to see them figuring it out in front of you. And to be fair, we've done a lot of it, so we often know what we're doing straight off the top of our heads, but that comes with practice and something that you can achieve too. Okay. Without using a calculator, find the exact value of this. Okay, these are somewhat more interesting problems. You can see here the 22.5. So 22.5, if you double that, you end up with 45, which of course is an angle in one of these special triangles. And we can work out the exact value for 45. These are 45-degree angles here. So the first thing really is to go and look at the angles here and to see what you're aiming for. So we're aiming for somehow to turn these into a 45. So again, you're seeing the distilled solution here. I'm going to start by actually expanding this square here. So I've got sine of 22.5 plus cos of 22.5, and of course that's looks like this. And now I multiply out, so I end up with sine squared of 22.5 plus 2 sine 22.5 cos 22.5 plus cos squared of 22.5. Now, why am I doing this? Well, sine of 22.5 and the cos of 22.5 go together, and they make 1, because sine squared x plus cos squared x equals 1. And then here, sine of 22.5 cos of 22.5, that is the double angle formula. In fact, the same one we used in the last one. That is the same as sine of 2 times 22.5. And I think it's fair to say it's unlikely you'll have done this in your head. You know, the only way you're going to get this is by experimenting with it, and when you eventually chance on expanding the brackets as the first thing you do, you'll notice you'll probably notice this first. This is very much the 2 sine x cos x. It's a double angle formula. And then, of course, you've got the Pythagorean one here. So solving this sort of problem is only going to happen if you're prepared to go down some wrong alleys. Anyway, here we go. We've got sine of 45 here. And if you go back up to our special triangle, sine of 45 is 1 over root 2. So we've got 1 plus 1 over root 2, and there we are. 5 marks for doing it without a calculator, and of course showing every stage of our working. Hope that was helpful.